Okay, in the last class we looked at the Patterson method, which is a method how you can find heavy atoms from X-ray diffraction data going around what is called the so-called phase problem. So in the example that we discussed, we have found a zinc atom within a crystal structure. Now that crystal structure contains more than only a zinc atom, so therefore our crystal structure determination is still incomplete, but finding the first atom is certainly a very big step forward. So what you can do now in order to find the other atoms is what is called successive Fourier synthesis. So you use the coordinates of the first atoms that you have found and calculate from that a structure factor. So that structure factor has an absolute value and a phase. So you discard the calculated absolute value because we have an observed structure factor also, or the absolute value of it in form of the intensity, which is much better than the calculated one, because the observed one contains all the atoms while the calculated one only contains the zinc atom. But we can use the phase, so this phase is still pretty much of a rough phase because it has been calculated only from one atom, but it's still better than not knowing the phase at all. And just from the X-ray diffraction experiment, you do not know the phase at all because you cannot measure the phase. So what you can do in the following is use the calculated phase and the observed absolute value of the structure factor and do a Fourier transformation to calculate a new electron density function. So that electron density function hopefully has new peaks that can be associated with additional atoms. So then the thinking process starts. You need to think about, well, which atom may fit on which maximum in the electron density function. You can place one or more atoms on these peaks, and that gives you additional coordinates for additional atoms. So now you have found already more than one atom, maybe another one or two or three. So now you can run another cycle, so you can again use the atoms and calculate a new structure factor, and again you can separate the new structure factor in its absolute value and the phase. So again you discard the absolute value of the structure factor, you only use the calculated phase, combine it with the observed structure factor, and do again the Fourier transformation to calculate now an even more refined electron density map. Okay, now you can hopefully identify even more atoms from the peaks on the electron density map. So you have again additional coordinates, and from these additional coordinates you can again calculate an improved structure factor, and you do this successive Fourier synthesis over and over again until you have found all your atoms. So for the lightest atoms you can also use difference electron density maps. So the lightest atoms are the hardest to find because they have the fewest electrons at which the X-rays can be scattered. But when you calculated the difference electron density map by subtracting observed structure factors from calculated structure factors in the calculated phase, then you can again find peaks, and these peaks can then be associated with the lightest atoms. So at the end of this process, you have a structural model for your crystal structure. But that structural model is still pretty rough, so the atom positions are still not very accurate. So for that reason, in the next step, you do what is called structure refinement, using a method which is called the least square method, or the method of least squares. So what you do here is that you slightly move the atoms around the position that you have found for it, and observe what happens to the difference between the observed structure factor and the calculated structure factor. Okay? So if the difference becomes smaller, then calculation and observation in closer agreement, and you have moved the atom into the right direction. If it becomes larger, then you have moved the atom into the wrong direction. Okay, so by trial and error, you refine the crystal structure using that method of least squares. So you do this until the difference between the observed and the calculated structure factor becomes ideally 0, but it will never become exactly 0. To see what is the quality of your crystal structure determination, you can use the so-called disagreement factor R, which is nothing else but the difference between the observed and the calculated structure factor over the calculated structure factor. So when the R value is sufficiently small, then you can consider your crystal structure sufficiently refined. So as a rule of thumb, you can say that when the R value is smaller than 0.1 or 10%, then your crystal structure is sufficiently refined. However, this R value does not give you full proof that your crystal structure is right. Very important is also that your crystal structure generally makes chemical sense. So at the very end, it's also very useful to check if the bond angles and the bond length are actually reasonable. So this is not always the case. So if that's not the case, then there must be a flaw within your crystal structure determination. For example, it could be that you have refined the crystal structure in the wrong space group. In this case, you may find that the R value is small, but your crystal structure chemically just doesn't make sense. Okay, this is the end now of the chapter about crystal structure determination. Now let us go to the next chapter, which is about close packed structures. So in this chapter we will discuss which crystal structures nature actually makes and why, and as the name of the chapter already says, nature tends to make close packed structure. Nature tends to minimize the space, empty space within structures, for the simple reason that the forces between atoms are attractive. So therefore nature tends to pack atoms in extended solids as close as possible. This is particularly so when the bonding forces between the atoms are non-directional. So that is the case for ionic bonding and metallic bonding, not so much for covalent bonding. For that reason we find the most exceptions from the principles of close packed structures for covalent bonding. Okay, so how can we develop an approach to close packed structures? So let us first look at two dimensions and ask, well, how can we surround a sphere representing an atom by other spheres so that these spheres are packed as close as possible? Because of geometric arguments, you can produce the closest packed structure when you arrange exactly 6 spheres around a central sphere. Because in this case, all the spheres, they touch each other. Okay, so now what would we need to do if we wanted to go from 2 dimensions to 3 dimensions? So intuitively, you would argue that, well, you just take another layer of these atoms and place it on top of the first layer so that the close packing is maximized. Now, in order to do so, you would place your second layer above the indents of the first layer. Okay, so you see these indents symbolized by blue and red dots. Okay, so if you place the atoms of the second layer above the red dots, then the space would be most efficiently filled. Alternatively, you could also place them on the blue dots, then the positions above the red dots would not be filled. Alright, so now what could you do with the third layer? And now you have actually 2 possibilities. The first possibility is that you place the third layer directly on top of the first layer. So that would mean that you've placed them above the indents here, 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 and here, and here, and here, and here. Okay? Then your third layer lies directly above the first layer. And you have what is called an ABA stacking with an AB repeating unit. Okay? The other possibility is that you place the third layer above these blue indentations here. Okay, then the third layer is offset from the second layer and the first layer, and therefore you have an ABC stacking. Okay, now the first case is associated with hexagonal symmetry. We call this kind of stacking the hexagonal close packing and the hexagonal close packed structure. It is associated with the space group P63 over MMC, and for the second case we arrive at a cubic structure with a space group FM3M. So you can see the stacking here more clearly in a little bit of a different view. So here you see the hexagonal close packed structure and here the cubic one. Here you see the AB stacking. You see that the second layer is offset from the first layer, but the third layer lies directly on top of the first one. And the fourth layer then lies directly on the second one again. For the cubic close packed structure, the second layer here in yellow is offset from the first layer, and the third layer is offset from both the second and the first one. Only the fourth layer lies directly above the first one. Okay, so now what are the unit cells associated with the hexagonal and the close packed structure respectively? So you see here a cell for the hexagonal close packed structure. So these atoms here in this hexagon, they represent the first layer. So these atoms here in this hexagon, which is centered, represent the third layer, which is identical with the first one, because you see that this hexagon lies directly above this hexagon. And then the second layer is represented by these 3 atoms here, which lie inside of that cell. So you can easily see is that this cell is hexagonal. So this cell, however, is not the unit cell. We have learned that hexagonal unit cells are always primitive, because in the primitive cell we can already see the 120-degree angle, which is characteristic for the hexagonal crystal systems. So therefore the actual unit cell is made only of, well, these 4 atoms, okay, and these 4 atoms, and only one of the 3 green atoms here is inside of the unit cell. Okay, so now you see here projection of the unit cell. Okay, you see that we have 8 atoms on the corner of that unit cell. Okay, and then we have an additional atom inside of the unit cell, and it's located at the position 2/3 in A direction, 1/3 in B direction, and a half in C direction. We have to go a half in C direction because the second layer lies exactly halfway in between the first layer and the third layer. Alright, so we have 2 atoms in the unit cell at the fractional coordinates 0, 0, 0 in 2/3, 1/3, and a half. Okay, so now what about the unit cell for the cubic closed packed structure? So in this case we have a face-centered unit cell. Therefore sometimes the cubic closed packed structure is also called the face-centered cubic structure. So in this cubic unit cell, the stacking is harder to see. It happens actually along the space diagonal within the unit cell. So these 2 red atoms, they represent the first layer and the 4th layer, which lie directly on top of each other. So these green atoms would belong to the second layer, layer B, and the blue ones would represent the layer C. Okay, you can see more easily that these blue and these green atoms belong to a layer in this version of the unit cell on the left hand side. So you see here more clearly that these green atoms form a layer and the blue atoms also form a layer, whereby the blue layer is offset with respect to the green layer. Okay, so now in this case we have 4 atoms in the unit cell, because we have our atoms that sit on the corners. Okay, we have 8 of them, but they only count 1/8 because they sit on the corner, so 8 times 1/8, that's 1. And we have our atoms on the face centers, so we have 6 of these, but each of them only counts a half, so that's 3, and 3 plus 1, that gives overall 4. So we have 4 atoms that sit on the fractional coordinates 0, 0, 0, 0, a half, a half, a half, 0, a half, and a half, 0. Okay, so here's another illustration of the cubic closed packed structure where you can see the layers more clearly. So this is the view of the unit cell that we have just looked at. Now what we can do is we can shift the coordinate system by a half. Okay, so for instance by half into this direction. Okay, then this white atom here would now be here in this position. So because of the shift of other atoms, we would create more white atoms here and here on the center of a edge. Okay, so these 3 atoms would represent the first layer. Then we would have more atoms on edge centers, these 6 ones here, plus an atom in the body center. So these atoms would represent layer B, and then we would have these black atoms on the edge centers. So these black atoms would represent layer C. Okay? So both unit cells are equivalent, they are just different views. In the second unit cell, the coordinate system is just shifted by a half in one direction. Okay, so now how well packed is the space in both HCP and CCP? And in both structures, 74% of this space in the unit cell is filled with spheres. And one can show that fairly easily using geometric arguments, and I want to do this here briefly for the case of the cubic closed packed structure. So you see here the cubic closed packed structure, the unit cell of it, and you see that in this cubic closed packed structure the spheres touch along the face diagonal. So the length of the face diagonal is the square root of 2. Okay? And therefore the radius of a sphere is, well, a square root of 2 times a. I should say a square root of 2 times a over 4. Okay? Okay, so now what is the volume of a single sphere? Well, it's the square root of 2 times a over 4 to the power of 3 times 4/3 times pi, because that's the formula for the volume of a sphere. So now we have to take into account the 4 spheres that we have per unit cell, so we have to multiply this volume by 4, and that value, which is the volume of the 4 spheres, has to be divided by the volume of the cubic unit cell, which is nothing else but the lattice parameter A to the power of 3. Now when you calculate this, then this gives exactly 74%. We could do an analogous calculation also for the hexagonal closed packed structure, and we would find that also for the hexagonal closed packed structure the space filling efficiency is 74%. So let us look at a few related structures. So let us look at what is called the simple cubic structure. So in the simple cubic structure, the spheres only occupy the corners of a cube, but there are no additional atoms. Okay, so certainly the unit cell content would be 1. We would have 1 sphere per unit cell. So you see that in this case the spheres touch along the edge of the unit cell, so therefore the radius of a sphere is the lattice parameter A, which is equal to the edge of the unit cell over 2. Okay, what is then a volume of a sphere? Well, a volume of a sphere would then be 4/3 times pi times A over 2 to the power of 3. So the volume of the unit cell would again be A to the power of 3, and the ratio would then be pi times 4 over 3 times 8, which is equal to 0.52, and the space filling efficiency would be 52%. You see that this is a lot less than the space filling efficiency of a hexagonal or a cubic closed packed structure. So finally, let us look at the so-called body-centered cubic structure, BCC. So in this case, you have an additional atom in the body center of the unit cell. So now, in this case, the spheres, they touch along the body diagonal through the unit cell. So therefore, the radius of a sphere is the body diagonal of the unit cell divided by 4. So the body diagonal of the unit cell is equal to this square root of 3 times a, therefore the radius is the square root of 3 times a over 4. Then the volume of a single sphere is 4/3 times pi times, well, the radius to the power of 3, which is the square root of 3 over 4 times a, well, to the power of 3. And the ratio between the spheres and the volume of the cell is 0.68 when we factor in that we have, in this case, 2 spheres per unit cell. Okay, so the sphere in the center of the unit cell fully counts, and then we have these 8 spheres on the corners of the unit cell, which count 1/8. So 1/8 times 8 gives 1. So overall 2. Okay, the space filling is strongly correlated with what is called the coordination number. So the coordination number is nothing else but the number of next nearest neighbors that surround a particular atom. So the greater the space filling efficiency, the greater the coordination number. So for both the hexagonal and the cubic close packed structure, the coordination number is 12. In the case of the hexagonal close packed structure, each atom is surrounded cube-octahedrally by 12 other atoms. And in the case of the cubic close packed, anti-cube-octahedrally by 12 atoms. And in the case of the cubic close packed structure, each atom is surrounded by 12 other atoms in a cube-octahedral way. Okay, so how can you understand that anti-cube-octahedron and the cube-octahedron respectively? You can put yourself on the central atom, and then you see that within the same layer, that central atom is surrounded by 6 other atoms. And then you see there are 3 atoms from the first layer and 3 atoms from the third layer on top and at the bottom relative to the central atom. So in the case of ABA stacking, basically the atoms of the first layer must lie directly above the atoms of the third layer. Okay, so that means that these 2 triangles here, they stand in an eclipsed orientation relative to each other. Okay, so that builds a cube-octahedron. In the case of the cubic close packed structure, this triangle here is rotated by 60 degrees relative to that triangle here, because we have ABC stacking, and that produces a cube-octahedron, what is called a cube-octahedron. Okay, so now what about the body-centered cubic structure? You can see here that in the case of the body-centered cubic structure, which is less dense, the coordination number is only 8. So each atom is surrounded in a cubic way by 8 other atoms. However, the next nearest neighbors are not much further away, so the distance between the nearest neighbors is half of the body diagonal of the cubic unit cell, which is a half times the square root of a, which is equal to 0.87a. The next nearest neighbors are, however, not much further away. They are 1 full lattice parameter a away. Okay, because we find the next nearest neighbors in the neighbored centers or in the centers of the neighbored unit cell, neighbor, this centers of the 6 neighbored unit cells. Alright, so what would be the coordination of a simple cubic structure? So we would expect that it's even lower, and indeed it's even lower. The coordination of is in this case 6, and each atom in the simple cubic structure is octahedrally coordinated by other atoms.